Hi, in this video we're going to continue talking about velocity and displacement. In particular, we're going to talk about relative velocity. So this is probably easiest to explain through an example, so let's have a look at one. So here we've got a bus traveling 20 kilometers an hour north. So we've got the bus, it's going 20 kilometers per hour. A person walks towards the front of the bus at 2 kilometers per hour. So they're walking north at 2 kilometers per hour. Determine the person's velocity relative to the ground. So they're traveling with the bus, they're traveling on the bus, they're doing 20 kilometers per hour plus another 2 kilometers per hour relative to the ground. So if I wanted to look at the person's velocity, we've got 0, 20, so that's 20 from the bus, plus another 2 from them, which gives 0, 22, or 22 kilometers per hour in the direction of north. The second part, if the bus is still going 20 kilometers per hour north, but in this case, the person's walking towards the back of the bus. So they're walking 2 kilometers per hour south. Now, in this case, relative to the ground, they're doing less than 20 kilometers per hour because they're traveling in the opposite direction on the bus. So in this case, for part B, we've got the bus's speed, we've got the speed of the person relative to the bus, and they're moving 18 kilometers. They're still traveling north with the bus, but they're not going as fast while they're walking. So when this is called relative velocity, so this 2 kilometers per hour here is the person's relative velocity. It's relative to the bus. And we want to work out what it is relative to the ground. So there's a little bit of calculation we have to do here. The rule is, and I'll move up for this, the velocity of the person relative to the bus plus the velocity of the bus relative to the earth equals the velocity of the person relative to the earth. So if the bus was doing 20 kilometers per hour north, the person was doing 2 kilometers per hour in the direction that the bus is going, then the person is doing 22 kilometers per hour relative to the earth. However, if the person was traveling in the opposite direction of the bus, then we have -2 plus 20, which will give us 18 kilometers per hour. Now, this is the case when a person is walking on a bus or a train. It's also the case if a person was to swim in the water. So let's imagine that a person in a swimming pool could swim, 10 kilometers per hour. So that's how fast they could swim in a swimming pool where the water is stationary. However, let's say they went into a river and the river was going at 5 kilometers per hour east, and they were swimming as fast as they could, but they were also going east. So in this case, they would have 10 kilometers per hour, their swimming speed, plus the additional 5, they would be swimming 15 kilometers an hour relative to the ground. If they were swimming in the west direction, however, then they're swimming 10 kilometers per hour relative to the water, but the water is pushing them the other way. So they're going to do 10 minus 5, they're going to do 5 kilometers per hour in the west direction. And the way you'd show that, so if we draw a little diagram of this, so we got north is up. So we got 10 kilometers per hour west. We've got 5 kilometers per hour east for the water. If I wanted to add these two things, we've got the person's velocity relative to the water. So we've got -10, 0, plus the speed of the water relative to the ground, That's like this component here, which is 5, 0. And that's going to equal the velocity of the person, relative to the Earth, which will be negative 5, 0, or 5 kilometers per hour in a west direction. So that's how we show this. Now, why is this important? Something like swimming speed, the speed that you can swim is relative to the water. So in a pool, if you can go 10 kilometers per hour, you're doing that relative to the water. You're also doing it relative to the ground because the water's not moving. However, if you're swimming in a moving current, then your maximum speed is relative to the water. It doesn't matter what the Earth is doing. It only matters what speed you can go relative to the water, because that's what you're pulling back when you're swimming, right? It's the same with a boat. The boat doesn't care what the water is doing relative to the Earth, right? We've got a boat and then we've got like a little motor off the back. All it picks up is how much water is sort of going through this propeller or impeller, I don't know what it is. So whenever we're talking about the speed of a boat or the speed of a plane, right? Again, engines with air going through it. A lot of these specs are how fast it can go in water or how fast it can go in the air, because that's what the motor is designed to do. Push the water through or push the air through. So often we'll have a relative velocity relative to the air or to the water, but what really matters is what the velocity is relative to the ground, right? Because that's how long it takes to actually get somewhere. So let's do another couple of questions to reinforce this. We've got a train is traveling 60 kilometers per hour north. A person walks across the train at 4 kilometers per hour in an eastward direction. Determine the person's velocity relative to the ground. So we've got a train. It's going 60 kilometers per hour this way. We've got the person is walking 4 kilometers per hour east. So east is to the right. So that's 4. We've got 60. We want to know what the person is walking relative to the ground. So they're traveling 60 kilometers an hour with the train, plus they're going 4 kilometers an hour this way. So we're adding the vectors together to get relative to the ground. And that's exactly the same as the equation that we had up here. We've got this velocity vector plus this velocity vector gives the velocity vector relative to the ground. So this turns out to be a simple addition of vectors problem. So we've got 0, 60, that's our velocity of the train, plus 4, 0, the velocity of the person relative to the train. We get 4, 60. So that's their velocity. Now we're often quoting in terms of the speed of the person and the direction because that's a more sort of understandable quantity. So the magnitude of the velocity is the speed, which is 4 squared plus 60 squared, square root. We get 60.13 kilometers per hour. This person is moving relative to the ground. We need their direction. So we're after this theta here. We get 3.81 degrees. And that's also the true bearing in this case, so equals 4 degrees true. Okay, so we've got the magnitude and we've got the direction. We'll look at one more example. So in this case we have a plane. It's traveling at an airspeed of 500 kilometers an hour northwest. So northwest, it's going 500 kilometers per hour. We've got a wind is blowing 60 kilometers per hour towards the east. So we've got our wind is traveling this way. Let's write that on here. So that is 135 degrees in there. Determine the velocity of the plane relative to the ground. So again, when we're working out relative to the ground, we're adding the other two vectors. So I'm going to draw my vector up here. We've got this is 60. And my velocity relative to the ground is just going to be the addition of the two vectors, or this third vector here. So let's call that V. V equals this vector, so that's going to be 500 cos 135. So that's my first vector. Then we're adding the second vector, which is 60, 0. And this is going to be the velocity of the plane relative to the ground. We get negative 293.55. And 353.55. Okay, and we can go ahead and convert that into a magnitude and a direction. Okay, so we've got the velocity or the speed, and we've got the direction. Now you can see that my diagram wasn't to scale, obviously, so this is the direction of the plane movement that I've got down here, and we've got the true bearing, and we've got the speed. So that's an introduction to relative velocity. Hope you enjoyed the video. I'll see you for the next one. This video accompanies a worksheet series that aims to develop conceptual understanding with vectors. If you'd like to access the worksheet, click in the description below.